Marshall Cross from MegaWave Corporation. We're a small business located at Fort Devens, Massachusetts, basically an antenna company. Been supporting Natick Laboratories, sponsored this work for the past about 13 years, and more recently been working on helping them to develop a wireless personal area system or network for the soldier, sometimes called a body area network. And I was going to say a few words today about measurements we've made around the human torso with a ballistic protective vest. The reason that, of course, they're interested in doing this is to eliminate the cabling between the different devices that an advanced soldier might wear: computer, radio, physiological monitoring, what have you. One caveat at the top, just want to make the point that I'm going to be speaking strictly about transmission loss and not path loss, difference being that a transmission loss includes antenna gains at both ends. And you can recover the path loss that you usually see quoted in a textbook just by knowing the antenna gain. The mode around the body, whether he has a vest or is just a nude, is probably a creeping wave. A creeping wave is a special case of slow waves or surface waves, basically guided or attached to the cylindrical object that it's creeping about. We've only begun to work on this. There are questions that remain. Is it a stationary process? Probably not, because the soldier is constantly moving. Is it dispersive? In other words, does all the energy at different frequencies arrive at the same instant of time at the receive antenna? Probably not. Is there a multipath delay spread? Probably. And Doppler spread probably is of no consequence. So we did this right. One of the systems that we're studying is ultra-wideband. Ultra-wideband originally was an impulse system, then moved to a multi-carrier. It's a very wideband system, typically 500 megahertz or wider. And the question is, when you measure loss measurements around the body between two antennas, is what you measure, which is typically a narrowband measurement, is it indicative of what you'd see at ultra-wideband? And I found this textbook by these two gentlemen. I don't think we know them. And it says, yeah, if you can tolerate the small error, then it's not a bad assumption. It's a reasonable assumption. And it's a good book, by the way. All right. The endpoints that we used on a phantom shown here, different combinations. In the arm, be going from his weapon to a computer on his back and so forth. Helmet. So these were different places we chose. The antenna that we used was down at the bottom. It's approximately 1 inch by 1 inch. It's a printed circuit antenna, and it covers the entire ultra-wideband frequency range of 3.1 to 10.6 gigahertz. Okay, the phantom was agar gelled filled phantom, which is more or less electromagnetically correct at these frequencies, 3.1 to 10.6 gigahertz. We had him in different positions. The left-hand side, you can see him with his equipment, typical equipment that a soldier might wear. In that backpack is a lot of his electronics, his radio, his computer, what have you. And you can see the wires going to the helmet. And what they're trying to do is eliminate these cables, like the cable that goes to the helmet. They have two things going on. One is the ultra-wideband system we're working on, and the second system is the wireless power transfer, where they'll send electricity to the helmet to recharge batteries for his display and what have you wirelessly. We had him in 3 different positions, standing, prone, and setting in a Humvee, which in my day was called a Jeep. And you can see the leads, the blue leads in the pictures going to the network analyzer. So we had two of these antennas that I showed you, and we're measuring the loss electromagnetically between the two of them with a device called a network analyzer. I had to throw in some double EM jargon here to counter the medical community with their jargon. I'm trying to help to get to lunch here. Okay. And I won't tell my joke about vice presidents of R&D either. Okay, this is sort of the result. Again, you see the frequency range is from about 3 gigahertz to over 10 gigahertz, very wideband system that's used. And these ultra-wideband devices you buy in Best Buy. They're dongles that you use in your home theater to connect up your video devices, HDMI and stuff. The transmission loss is plotted here as a function of frequency. And the message from this first slide is the amazing result is that the loss around the body is actually less when the soldier has his populated ballistic vest. And he doesn't wear lead things. He wears boron carbide and composite ballistic plates around on the front and back. But we have less loss between the two antennas, depending on the position. And this is an average of all positions that I showed you. Okay. When he's prone, I just plotted 2 here, just with the protective vest, and forgot about being naked. And you can see, again, the loss. And generally, there's a trend. It's increasing with increasing frequency, as you would expect. And finally, we sat him in the Humvee, the vehicle. One amazing thing about this measurement is it's slightly less than when he's in free space, the theory being that the energy is sort of constrained by the vehicle. You're sort of in a cavity, if you want to think of it that way. Okay, conclusions. Oh, I'm going to get you out of here. The magic number is 83 dB. That's a I know none of you are going to remember that this afternoon. We found less loss when the vest was on the populated Phantom filled with seaweed versus when he was nude, which gives more credibility to the whole theory that this is really a creeping wave mode that's going around the body, because the difference in dielectric materials in the vest is helping to guide this wave. We saw a little difference between standing, prone, sitting in the vehicle. Just using dongles that you buy at Best Buy for $50 a pair. We tried these off-the-shelf things. They work